Check. Okay, let me start. Welcome to the 12th class meeting. We were here in this paper entitled Capacity of Second-Order Cyclostationary Complex Gaussian Noise Channels. Last time, I reviewed the definition of propriety and impropriety for a random variable. And this definition easily extends to the random vectors, random matrices, and also random processes. And extension is very straightforward as far as you know how to extend the notion of real random variable up to real valued random processes. And there was another interesting definition about the second order central moment of a complex random variable. And here, the variance is computed by the expected value of the absolute value square of the difference between the random variable and its mean. And complementary variance or pseudo variance, to the contrary, has parentheses squared. And this makes interesting observation that the ordinary variance only contains the self-variance of the real part and self-variance of the imaginary part. However, the complementary variance has what? Not only includes the information about the difference between the real and imaginary parts variance, but also covariance. Last time I didn't have enough time to talk about the interesting parts. And as you see here, since the pseudo variance is in general complex valued, the statement that the pseudo variance of a complex random variable vanishes or equals to 0 actually is equal to the two scalar equalities. What? The first is the real part is 0 and the imaginary part is 0. So the real part of the zeroness of real part means that the variance of the real part and the variance of the imaginary parts are the same. Second, the imaginary part is 0 means covariance is 0. And here goes some example you must remember. Suppose the real and imaginary parts of a complex random variable is generated by a real Gaussian random vector with identical variances and 0 cross correlation. Okay, it seems that this is too changed. Hello? Okay, got it? So suppose you have this case. Then what is your expected value of the complex random variable z, that is the summation of x plus jy? Then you have this is mu x and mu y. So you have mu x plus j mu y, that is mu z. And now, what is your variance? Variance of z is simply variance of the real plus variance of the imaginary part. So you have 2 sigma squared. And what is the complementary variance? That is 0. And by the way, what is the probability density function of your complex valued random variable? Since this is nothing but the density function of this one, precisely speaking, you have to consider two variable function. So it's just same as what? The product of the real part PDF and the imaginary part PDF. And you have what? 1 over square root 2 pi sigma square e to sigma square negative x minus mu x squared times the same coefficient because the variances are the same. And interestingly, you have here this form. By the way, sometimes we just want to say this is sigma squared. In that case, we need to scale the variance. So more popular form of complex Gaussian random variables, PDF, is what? 1 over pi sigma square e to the negative z minus mu z magnitude squared divided by its variance. Got it? And also, let me remind you what is the contour plot of your complex Gaussian random variable. Suppose this point on the complex plane is a complex number representing mu sub z. In that case, due to the circular symmetry of your PDF with respect to mu sub z, what you will see is something like this. So you have concentric circles that represents the PDF of this Gaussian random variable. Now, don't be confused that the circularity of a density may imply, not always, may imply the, actually implies the propriety, but the converse is not true. What I mean is that the propriety of a complex random variable does not imply circularity of the density in general. So you may have some lemma. If your complex random variable, not necessarily Gaussian, can be written as so suppose that your complex random variable has circular PDF, circularly symmetrical PDF with respect to 0. So you have taken its mean out. So again, the case similar to that one. Got it? Now, The question is, can we say that? So if the density of Gaussian random variable is circularly symmetrical with respect to its mean, so we assume the existence of its mean, then is it proper? So how can you prove it? Anybody? So the best way is to use the definition. So consider the complementary variance of Z. What is it? So after we subtract the mean, we just need to square the Z of 0. Then what? Then yeah, I remember I had a very neat proof about this one. Just a second. Yeah. So circular means that with arbitrary rotation angle theta, so let's define some new random variable z1 as z0 times e to the j theta for any theta. Then what do we need to have? Due to the circularity, we must have something like this, right? Now, let's think about the complementary variance of Z1. Then what do we have? We have got it? Because Z1 and Z0 has the same PDF, their moments must be the same, right? Now, we have the relation that Z1, a complementary variance of Z1 is nothing but the complementary variance of Z0 times e to the j2 theta for all theta. Then what can you say? Just plug in theta equals pi over 2, or you may put theta equals 0, then they are the same. Also, so the idea is like this. A complex number is same as another complex number after any rotation. Intuitively, suppose you have some complex number and rotate this complex number with any angle, and you want to have identity to some other complex number. Got it? Then intuitively they are zeros, right? And you can easily prove by substituting two different data values. Then you have two equations and two unknowns. And by solving that, you can show that they are equal. Got it? So what I would is that I would plug in theta equals 0 and theta equals pi over 2, something like that, to obtain two equations with two unknown complex numbers. And you solve it, and you can show that they are the same. Got it? So in this way, this is true. Got it? So if you have a circular PDF, circularly symmetrical PDF, and if complex variable, random variable has mean, that is important, because if the mean does not exist, you cannot talk about its variance or pseudo variance, because the definition requires the existence of the mean. Got it? So the lemma says that if you have a circularly symmetric density for a complex random variable that has its mean value, then it is a proper complex random variable. Because of this lemma, our previous example of a complex Gaussian random variable having the same variance for the real and imaginary parts and zero cross-correlation coefficient is what? Because of that derivation, we have a circularly symmetrical density, so it's proper. You can also show by using the algebraic definition, it is proper, right? So whenever you have some definition, as an engineer, try to figure out not only the algebraic definitions, but also some geometrical interpretation or geometrical meaning of the definition. In that case, you have instant understanding of what's going on. However, this geometrical something sometimes fools us. And also, we have to be very careful about if and only if. Here, the lemma says, if we have circular symmetry, then we have propriety. However, as I told you, the converse is not true. And you can just come up with any example if you wish. So I will not talk about it. But again, for Gaussian real and imaginary parts, that is true. Got it? So sometimes this propriety and circularity is often confused because some textbooks and papers define circular random variable by using this definition of propriety, but never do that. Got it? Because they are different things. And the difference is very clear when you extend the idea of propriety from a complex random variable to complex random vector. So consider a random vector z. Then what is the meaning of propriety? So we first assume the existence of its mean vector. And even though it's very confusing, let me just use mu sub z underscore. And of course, I want to write it this way. Yeah. So mean vector exists. And now, instead of using variance, we need to use covariance. And what is the definition? Z minus mu z Z minus mu Z Hermitian transposed. And what is the complementary or pseudo covariance of this Z vector? And you have ordinary transposition. Now, can you do the same thing for this vector valued complex random variable or complex random vector? Yes, you can. So we call x underscore as its real part real random vector, and y underscore as the imaginary part random vector, real random vector. Then what? You can plug in these two. Then what do you have? You have the covariance as in terms of covariance of x, covariance between x and y, and covariance matrix of y, and also complementary covariance as what? In terms of these three things. And the definition of propriety of this C is what? Complementary covariance matrix becomes zero matrix. Let me use this kind of bold-faced zero. And you can show that this implies, sorry, this is equivalent to that the covariance matrix of real part random vector and the covariance matrix of imaginary part random vector are equal, and cross covariance matrix vanishes. So here, this identity of the covariance matrices must be paid attention to, because here goes different definition of circularity of a complex valued random vector. Circular means that if you wish CDF, it really means the high order PDF, the PDF of Z vector is the same as what? PDF of Z vector times e to the j any angle theta. Got it? And now it becomes very, very clear that they are different. Not only in that circularity is about the shape of the PDF, and propriety is about the property of the second order moments. Got it? Now, can we establish the same lemma? Saying that if Z is circular, then Z is proper. We can do that. And that's not that difficult. However, the converse is definitely not true. The first reason is that the definitions are totally different because one is only about the second order moments, but the other is about the shape of the PDF. Got it? But circularity and propriety is very quite often confused because in many cases, we work with Gaussian, complex Gaussian random vectors. So let's focus on complex Gaussian random vectors. First, what is a complex Gaussian random vector? So it's real part random vector and imaginary part random vector when they are stacked. If this twice length real random vector has a Gaussian distribution, then we call Z is complex Gaussian. Now, here goes the definition. So if a complex Gaussian G is proper, then we have very nice compact form of its PDF when covariance matrix is invertible and anybody. So if you get confused about the multidimensional Gaussian density, then consider some extreme cases. And we know that if the size of Z is 1, then we should have what? Right? And what if we have independent components, especially having different variances? In that case, our answer should be what? Product of these things with different variances. So probably we have something like this. Since we already know the answer. So here goes the answer. Got it? So as you see here, if n equals 1, then you have the density of proper Gaussian random variable we just derived. Got it? And for the case where we have independent components, then covariance matrix must be diagonal, and determinant of a diagonal matrix is the product of diagonal entries. So we have this one. And also we have the product, how to say, summation of G sub I minus mu sub Gi magnitude squared divided by sigma sub I squared summed over, and that corresponds to this one, as you learned in the linear algebra. Got it? So we have very parallel form with real Gaussian case. In real Gaussian case, what do we have? Got it? So this is for real Gaussian. And this is for what? For complex proper Gaussian. Now, what about improper Gaussian? Unfortunately, it's not that easy. One method would be using the PDF of the stacked version of the real random vector and imaginary part random vector. Got it? So as you see here, the similarity of the form of PDF ends with the propriety. Got it? And if you look up some textbooks, just talks about vaguely about complex Gaussian random vectors, some textbooks mistakenly or ignorantly states that this is the PDF of complex Gaussian random vector, which is partially true. It is true only when the Gaussian random vector is proper. And if it is not proper, you cannot use this form of PDF because there is no correlation information such as this one in this form. Got it? So people have devised a notation saying that X follows a distribution of normal with mean vector X and covariance matrix C. And here N means normal. That is for real Gaussian. And for this complex Gaussian case, people have devised this method. And it's also very, very misleading because C means complex, N means normal, and it gives us misleading notion that to characterize or fully describe a complex Gaussian random vector, we need only the mean vector information and covariance matrix information of Z. Got it? Actually, if I am the guy who can dictatorially say, hey, this is wrong, complex, proper, normal, then this would be a better notation. But nobody used this one. So whenever you see in a research paper or textbook, some notation like CN, right? Then assume Z is proper. Because what are three parameters that fully characterize a complex Gaussian random vector? It's mean vector and covariance matrix and complementary or pseudo covariance matrix. So better notation would be something like this. And if you want to really emphasize it's proper, then you can just put what? Big zero matrix here. Then showing that your covariance, complementary covariance matrix vanishes. It's a zero matrix. Got it? So anyway, we have just reviewed the definition of a proper complex random vector, and also its implication in the shape of the PDF. And we know that it does not imply any shape. Circularity, to the contrary, means something, but it's too strong for the one-dimensional case. By the way, in multi-dimensional case, what kind of transformation would correspond one-dimensional rotation? As you learned in linear algebra, rotation in two dimension can be written as what? Rotation matrix, right? So you take the x, y, and you multiply cosine theta, sine, negative sine, something like that to mean the rotation transformation. What about in 3D? You have 3D rotation. You can extend it into any multidimensional, including reflection with respect to some axis. What is that? Unitary transformation, right? So any unitary transformation can serve as what? Something equivalent to rotation in one dimension. So if the circularity in one dimension was to be extended, there could be two ways. The first one was that just as we did, multiply e to the j theta. So in n dimension, as I have shown you, and most of the researchers do that, this is the simplest extension of this one-dimensional circularity definition. Z and Z times e to the j theta has the same distribution or has the same shape, okay? But another direction would be what? Z and any unitary transformation, of course, with respect to mean. So let me be careful. So by the way, yeah, I should have told you. Yeah, something was not correct. By the way, there is another definition. Some people mean circular implies Z minus mu Z e to the j theta has the same PDF. Similarly, where is circularity? Yeah. So this circularity is actually means z minus mu z e to the j theta has the same distribution, right? So there are not consistent definitions about circularity. That's what I mean. Got it? Got it? So whenever you see circular random variable, circular random vector, what is my message? Be careful. Try to find out what is the exact definition the author of the textbook or the authors of the paper mean with circularity. Got it? Because there are too many different definitions. Some people really mean propriety. They even don't talk about the shape of PDF. Got it? So be alert. That's why I really hate using the terminology circularity in any of my research paper. I do not want to add one more confusion to the full of confusions. Got it? Okay, so I believe I talked enough about the kind of preliminaries. So let's go directly to the to this paper, capacity of second-order cyclostationary complex Gaussian noise channel. The idea is very, very simple, but need one more new result. That was the most important contribution of this paper. And also, I believe that is one of the most important contributions of my research group, because the result was never observed or reported in any publication. So first, as I confessed, I didn't assume impropriety. I also wanted to publish the paper very quickly, and especially showing that, hey, we can exploit the excess bandwidth of that appears to be wasted in the satellite communication. And I wanted to show that we can take that back to put one more stream of data so that we can fully utilize the spectrum band. So initially, what? The ambient noise and interference, both what? Both proper complex Gaussian random processes initially. And as you know from the previous techniques, especially the vectorization, you can immediately transform this signal and system model into what? Here, what is x vector of t? Vectorized Fourier transformation of x. What is this h underscore t? Vectorized Fourier transform of impulse response. Same. Now, this is nothing but what? Because summation of two independent Gaussians are what? Gaussian random variable, right? Vector valued Gaussian random variable. And also, what is the property of this one? If we choose the Nyquist drawn for our vectorized Fourier transform corresponding to the cycle period of this one. Then this is a Y-sense stationary Gaussian random vector process. So everything becomes just what? Just MIMO channels capacity problem, as you learned in some other textbook. And the better thing is that what? This channel impulse response matrix is diagonal and square. Everything's simple. So what you need to do is what? You transform that one to a discrete time version and you do water filling. So it's just a piece of cake after you define, you show that if you choose, so we assume that this interference is cyclostationary with cycle period t, and this is Y-sense stationary. And Y-sense stationary random process is cyclostationary with any period t. You can show that. Okay. Okay, I will show that soon. So summation of these two are also cyclostationary with cycle period t. That's why when you vectorize Fourier transform all of the signals and random processes, you use the Nyquist drawn of length 1 over capital T. Got it? Okay, so let's show that. Very simple consequence. So here n is assumed complex, proper complex random vector, random process is Y-sense stationary. Then so we want to show this one. What is this one, by the way? You subtract the mean function that is constant, right? Because we assume the Y-sense stationarity. And what? So this becomes covariance or correlation, same as correlation, covariance. Let me see, let me use just correlation. Yeah, it's very confusing. So how can we show this? Y-sense stationarity means what? Y-sense stationarity means autocorrelation function is what? Is the same as the autocorrelation function evaluated at the time difference, comma 0 for all Ts, right? So Let's start with and ends up with what we wish to prove, right? Got it? So here, complex is used what? For this conjugation. And many of you may wonder, where did we use this propriety? And here goes some unfortunate story about the definitions of propriety and Y-sense stationarity and things. Because Y-sense stationarity of a random process, whether random process is real or complex, was developed before people have noticed that we had to define propriety or impropriety first. So most of the definition about complex Y-sense stationarity only rely on what? Again, mean and autocorrelation function. I really hate this because if I was the person to do everything I want, probably I would have put the third requirement, and that's about the complementary autocorrelation. But this is totally missing in almost every papers and books so far published. So I myself also just conform to this convention. So this third property is omitted in the definition of Y-sense stationarity of a complex random process. Okay? Got it? However, if I put propriety, since this is 0 always, so it justifies omission of the third line. Got it? So when you talk about Y-sense stationarity of a complex valued random process, be careful, especially when your process is improper. Got it? So as far as I remember correctly, when I define improper complex random processes Y-sense stationary, I put the third line always. Because this complementary autocorrelation does not vanish in general. Anyway, so now you understand why this paper was originally submitted as a part 1, part 2 papers. Because theory was too simple after we introduced the vectorized Fourier transform. And actually, the vectorized Fourier transform was just named by myself before people never used, because it just gave it was related the idea of harmonic series representation. But we needed to call the system that transforms a scalar valued 1 to vector valued 1. We just named it. So the reviewers also pointed that out. Hey, the contribution is just putting the name to that transformer. And after that, this very simple signal and system model is what? Equivalent to this vector matrix model, and its capacity is well known. By the way, how can you find the capacity of this one? That is actually another question, because most of the textbooks talks about the capacity of a MIMO system, assuming that they are given what? A discrete time memoryless channel whose input-output, X and Y respectively, are related this way. So X is the input vector. And of course, this is very misleading notation because X is random variable. But anyway, you mean what I mean. You know what I mean. And Y is output vector of length n, which means H is channel matrix m by n. And here comes complex valued Gaussian random vector with mean 0 and covariance matrix C sub nn if you want. Okay. Now, do you know how to derive the capacity of this channel? Discrete time channel, discrete time memoryless channel. In order to derive the capacity of this channel, you need to do what? Decompose the channel matrix using singular value decomposition. So you need you have some properties like this. So a general rectangular complex valued rectangular matrix H is now written as the product of three vector matrices. The first one and last one are both unitary matrices, and the middle one having the same size as H is what? It's kind of diagonal matrix. Even though it is general rectangular, only diagonal entries could be non-zero. So this is not that good notation because some j can, yeah, anyway. So if I equals j, then you have some non-negative value. And if I different from j, they are zeros. So seems okay, right? So I ranges from 1 to m, and j ranges to 1 to n, if I remember correctly. Yeah, this will work, I believe. And if I talk about singular value decomposition in detail and its implication and application to this capacity, then it will take up more than 2 weeks, which I do not want. So let me just give you a special case where H is diagonal. So in that case, what can you do? See that H is in general complex valued. But here, SVD requires what? The realness of this sigma matrix. But as far as you have unitary matrices, it's okay, right? So suppose you have H1 e to the j phi1, H2 e to the j phi2, dot, 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 M e to the j phi m. What would be a good singular value decomposition of this H? By the way, singular value decomposition is unique in the sense that after some reordering of column vectors of U and V, you have almost the same thing, except some complex some rotation angles. So here you will see what? Sorry about that. So the magnitude of the first entry and phase of the first entry. So you put the magnitudes here, and what do you want to do about the unitary matrices? Actually, there are uncountably infinite choices. As you see, you can put, for example, do you understand what I mean? So as far as you choose U and V diagonal, then this one is simply the product of these three things after you change this Hermitian transposition as conjugation. So you can choose arbitrarily. This is arbitrary, okay? Arbitrary choice. So I just have chosen the 1, 1 entry of U matrix as the e to the j phi1 and 1 here. So if you multiply these three after conjugating 1, you have that back. Second term, same. Third term, negative, for example, 2 phi3, magnitude of H3. Now this becomes plus J3 phi3. You add up, you have the third. And anything could be possible, like you have e to the j phi4, j, not j, plus some theta, arbitrary theta 4, and you have that arbitrary theta 4. In that way, how many unitary matrices, the singular value decompositions can you have? Uncountably infinite. So this choice is not unique. However, it's somewhat unique in the sense that after you properly rearrange the order of these things, then they are merely rotations or sometimes reflections. For example, you may put negative signs here, right? Anyway, so in diagonal case, everything is very simple. And what's interesting is that if you have taken the graduate level communications course or advanced digital communications course, you know how to derive the capacity of the MIMO Gaussian channel. First thing is that probably you just assume that this is white noise. So the additive noise is white. Then what is the capacity? C, bits per channel use. Anybody? Log determinant. What? Then you need water filling here, right? So you need to solve optimization problem. So maximize this log determinant with respect to your power level. Not exactly. So after decomposition, in this case, sigma squared is the same. So you have what? Yeah, I would not say this. Okay, because it's white already. Got it? So something like this, assuming that the input random vector has norm P, something like this. And to derive this one, you need what? You need singular value decomposition. So sigma sub I, no, this is not right. Let me use, where is the singular value? Yeah, okay. Yeah, it's very confusing. So sigma is variance of Gaussian noise. Sigma sub I is related to the singular value. Yeah, I'm not quite remember, but probably it looks like this one. Okay. And now we need to extend it to the case where you have positive definite covariance matrix. Then what can you do? Now it becomes complicated because first, what? You need to whiten the noise. So we need Cholesky factorization, or equivalently, in this case, eigenvalue decomposition of this matrix C. So suppose you have, let me use V, D, V Hermitian transpose. So here, these are eigenvalues of this positive definite matrix C. And again, V is a certain, V is the unitary matrix that contains all the eigenvectors. And they are properly normalized so that V becomes a unitary matrix. By the way, if I use V, then everything would be confusing. So let me use something different. W. Okay, let me use W. So these vectors are normalized eigenvectors of the positive definite matrix, Hermitian symmetric matrix C. Then what do? You have originally this observation matrix, observation signal model. Now here you put whitening transformation that is motivated by this eigen decomposition. So here, what he put is so-called the negative square root of this C matrix, which I'm going to define. Then what do you have? Here, the older diagonal entries of the diagonal matrix is replaced by its square root reciprocated. So you can easily see that the noise part, the noise component N is what? Is now C negative 1 over 2 negative square root times N, which is what? Which is zero mean white noise. Since this C is by the way, do we need to whiten it or just make it uncorrelated? Just a second. Yeah, I remember we don't need to whiten it. Yeah, it's okay anyway. Yeah. And you see our new observation model, Z equals C to the negative 1/2 HX plus C to the negative 1/2 N is nothing but a new signal model that can be just written in this form, where H tilde is what? C to the negative 1/2 H, which is another rectangular matrix. So X vector has some power constraint. Still, you can singular value decompose H tilde matrix to find the capacity of this MIMO channel by using water filling. Okay, so for each sub-channel that is independent, then what you do? You do water filling. You have parallel Gaussian channels So you can find the capacity of this case. Now, especially when we have colored noise and diagonal cases, then what? We need whitening. So let's take a look at this H tilde. Unfortunately, whitening filter has, in this case, matrix that works on, for example, diag H will give you non-diagonal matrix. Just a second, am I right? I believe so. Yeah. Let me give you an idea. Suppose this, in general, this whitening matrix is not diagonal. So you have some column C1 and column C2. Then what? You multiply diagonal entry. Then what? This times that one. Yeah, am I right? E1. Yeah. So actually, you have something like this. Yeah, something like this. So you don't have diagonal terms. Got it? So even though in our special case is similar to the case where we have a square channel matrix and diagonal entries, since we have non-white noise, after whitening, we have general MIMO capacity problem. The only difference is that we still have square matrix. Got it? Because H is square. Anyway, so let's briefly see the procedure. Okay, time's already up. So you see, there is something, just to forget about this F and T. You see the whitening matrix. So we need whitening anyway. And then we need water filling. As you see here, we need water filling. Got it? And with summation of log 1 plus something that is related to the SNR. And we need to convert it back to have our input distribution. Anyway, so that is the idea. You see? Whitening filter, H matrix, noise, right? And this noise is now white. And finding the capacity of this channel from X to Y tilde is just simple. That's why part 2 approach failed. They said, hey, too simple. Okay? So on this Thursday, why this paper survived? How this paper survived that harsh critics? by just adding one more assumption of general complex Gaussian channel, possibly improper cyclostation. Got it? So let's see that result next in the next class meeting.